This is our graphic syllabus that I showed you at the very beginning of class to see where we are and where we're going. And we were here in the beginning with all the basics from algebra to geometry to pre-calculus to calculus 1 and calculus 2. So that's the beginning part, and that's what was expected of you. And then we dealt with vector valued functions. First we studied vectors, and then we did some basic algebra and arithmetic with vectors. And then we took the derivatives and integrals of vectors with projectile problems, tangent vectors, and things like that. And so all that stuff was covered under the idea of vectors. So today we begin with our multivariable functions. And we're going to take derivatives and integrals of multivariable functions. And the derivatives will be in the same section or same chapter as the introduction, and then the integrals will be in the next section, because they require a lot more information, a lot more ideas and concepts that are new. The idea of derivatives in the beginning would be simple, and then we start applying more derivative ideas, and then it gets a little bit more complicated. But somebody decided to save the integrals for another chapter, so that's what we're going to do. So this is where we are. This is where we are now. Okay? All right. So, an introduction to vector or functions of more variables, 2 or more. It says here 2 variables, but we can also look at it with more variables. And this is a piece of notation that I like to use that will give us an idea of what type of function we're dealing with. So back in pre-calculus, and also in Calc 1 and Calc 2, we had y as a function of x. So we had functions that look like this. F is the name of your function, and it takes a real number, usually denoted by x, and then it sends you to an output, which is also a real number, usually denoted by y. And so the notation that we use is y is equal to f of x. So some examples of this might be y is equal to x squared, or f of x equal to x squared. And so either one of those, we're familiar with either one of those notations, and that's how they're going to get to be interchanged here. When we dealt with vector valued function, or sometimes we just call them vector functions. We kind of have a similar idea or similar notation. First of all, I often use the symbol R to represent the name of your function. So R with an arrow on top, or a vector R, is going to be like our F kind of thing. And R takes as an input a real number, which we'll call T. And then it outputs, well, depending on whether you're 2 or 3 dimensions, it outputs a vector. So it gives you an XY value if you're in 2 dimensions, or an XYZ value if you're in 3 dimensions. And mathematically, we can go as many dimensions as we want. We can introduce 2, 3, 4, or 15 more variables as part of your output, so we get this long vector. So the notation that we often use is R of t is equal to a vector x of t, y of t, z of t if there is a z of t. And our example might be the helix or something. Just so we get a feel for how this looks like and what kind of notation that we use. So this is stuff that we've done in the past. So now we're looking at a new type of function that's going to have this form. So let's see if we can set it up the same way we've set these two things up onto our new function of 2 variables. All right, so two variables seems a little restrictive, so 3 or 4 or 5, we can have as many variables as we want. So the notation that we use here, we use little f again. Seem to be running out of letters in the alphabet. And instead of taking a scalar for your input, you're actually going to input more than one number. 2 or more or more. But regardless of how many you put in, your output is just going to be a scalar, just a real number. Or I guess we're dealing with real numbers here, but technically it could be complex, or it could be some other weird number. So that means your input takes in a pair or a triple or whatever, and then it outputs just another number. And usually if you have a pair of numbers, the output would be a z, and if you have a triple of numbers going from R3 to R, the triple is usually described as an XYZ, and then your output is still a real number, and so they just use, sometimes they use W, or sometimes they use other numbers. So the notation that we would use in terms of carrying this notation out, sometimes, you know how we had y is equal to f of x? Sometimes we might say z is equal to f of xy. Or if you're going from R3 to R, and sometimes we say w is equal to f of x, y, and z. Now, there's no written rule that says we have to use x and y. We can use any number we want, or z, or w. But this is just the standard. So we can come up with some weird examples, or interesting examples. Simple examples. I don't know if this would be simple, but x squared plus y squared would be an example. Or if you have three of them, w is equal to x squared plus y squared minus z squared, or something like that. So those are just other weird functions. They're not weird. We'll get to some weirder functions later. But in terms of a comparison between what we've done before to what we're about to see now, this is a little bit of a preview of what we're looking at. Okay? So there's different ways to express these things. We can express these things with formulas like these, or we can come up with some other weirder thing to express them with. So, this, by the way, we've seen this already, right? You know, remember what this was? What is this? It wasn't on your test. Close, no? If z was just the number, then it would be a cylinder. No? Close. Getting warmer? What? No. The cross sections are circle, whatever cross sections mean. We'll talk about cross sections in more detail. No? No? No. What? Elliptic or circular? More like circular. Paraboloid. So it's a paraboloid. So it's not a cone, it's not a circle. It's a paraboloid. Okay. So paraboloids, cones, hyperboloids, those are, and spheres and stuff, those are basic shapes that you're going to need to be able to pull off the air. Just if you have an equation, you look at that and say, oh, that's a paraboloid. Or if somebody tells you come up with a paraboloid, then you need to come up with an equation. So it's one of those basic shapes that you're going to need to know. And I know I didn't have I didn't include that as part of the test, like the quadric section. But it's something that you should know. Because later on we'll need to come up with these shapes, with equations of these shapes, and you need to make that relationship. All right. So an example of a possible example would be a contour map. There's this map over here. says the predicted high temperatures. This is really blurry. I wonder if we go here, get a nicer picture. Am I connected? Oh well. I'll just take the picture that I have. Let's try to make the most out of this. So this is a contour map. And this is one graphical representation of a function of several variables. Let's say one of several ways to represent a function of several variables. And for this particular example, I may want to use, still want to use x and y for my input. And then maybe my output be something else, maybe a z. But when I think of z, I think of up and down, so maybe I might want to use something a little bit different, like maybe t or something. And so I would probably write this as t of xy where t stands for temperature. Okay. So how is this a function? First of all, do you know how to read this graph? Do you know? The color sections with a key. Okay. It's all blurry. You can't see.
Well, since it's weather and temperature, it's pretty safe to assume that the closer to red,
The hotter it is.
the hotter it is.
Okay. So let's pick a. Let me pick a point. Let's go to North Dakota. Okay. So give me some examples of values in North Dakota. Whatever that means. What's the longitude and latitude of Bismarck? You guys want to put that up in your phone? Find it. Why did I ask for longitude and latitude? What?
It's having some trouble with the connection. Please try again in a moment.
Bismarck, North Dakota is 46.81 north and 100.77 west.
Okay, so I just asked for longitude and latitude. Why would I ask for longitude and latitude?
That's the way your GPS works.
That's the way your GPS works, right? And that's a good way to look at a map. So
Use it as a phase substitute for x and y.
for x and y, so maybe x, x latitude, longitude. So maybe x could be your longitude, and then your y could be your latitude, 2 t's, right? So as an example, maybe in North Dakota, Bismarck, ND, our longitude was what? What was it, Jesus?
For 46.8 grams.
And our latitude, actually that sounds like the latitude. Y equals what?
123.78.
Okay, so I'm going to switch these two because I think when you said north, that I think of the y-axis. So, what is it? 10.
100.78.
So the x and y that you would have as an input would be these values, the longitude and latitude. And then your output so t, when we put in 100.78 and 46.81, would give an output of whatever the temperature is here. So that's probably really cold. This is in June. I can't even see that. I'm just going to guess 70. So we can say that the output would be 70 in this case. Okay? Does that make sense? So we use a color-coded map, also sometimes called a contour map, as a graphical representation to represent a function of several variables, a function of two variables in this case. And you remember the idea behind a function? You have an input, and then your output is going to be a unique output. It says that your output is going to be 70, and if you were to put this into your formula again, it's always going to be 70. It's always going to be the same output. Okay? So that's one way to represent a map or a function of several variables. What's this contour map? Oh, here's another contour map. Have you guys seen something like this before? You sometimes don't see the bottom picture. If you look at a contour map, like an actual map, you tend to just see the top picture. This is your contour map. And much like that shaded map, this is the same thing, except it doesn't have a shade. It still has those lines, kind of like this one has these lines over here to represent the contours. And then they just color it in to say, oh, it's darker over here, so it's colder. It's lighter over here, so it's warmer. That kind of business. Except over here, it's the same thing, but with no color. Instead of color, they give you markers, like 50, 40, and 30. So if I was going to say, take an example of a point here, I'm going to call this AB. That's a two-dimensional point on this map. And let's say the function was, let's call it f. What can you say f of AB is equal to if you're looking at the contour here? So not quite 10. Between 10 and 20 would be a better description. I was going to say 15, but it may be 13 or 14, 15, 16, 17. So it's between two contour lines. It's between 10 and 20. So we could say 15 if we can agree that that's a number between 10 and 20. Okay? So these are a couple of graphical representations. Another one that's hard to visualize would be, we'll go back to the idea of temperature again, but just to give another example of space and temperature. Let x, y, z be a point in space. So a point in space, let's say this room, and let's put a corner for the origin. Let's say this corner is the origin, right? The bottom corner. So this is x, this is y, and z goes straight up. So this is the corner of the room. And then you pick any point in space, and let's just say, to make things a little bit more interesting, there's a heater over here. So there's a heater that's on over here, so it's really warm in that corner, right? And then as you get further and further out, it gets a little cooler and cooler. So the question is, if you pick a point out here, let's call it A, B, and C, as a point, you can ask yourself what the temperature is at that point. And maybe the temperature is some radial distance. As you go further and further out, it gets warmer and warmer. So I'll just make up a function for that. And this would be x squared plus y squared plus z squared. So now I have some sort of graphical representation of a function of three variables. Now in this graphical representation, I have space, x, y, z, and a, b, c, right? So that's a point in three-dimensional space. Now the temperature gives it a fourth dimension. And it gives a relationship between the temperature and the x, the y, the z coordinates in space. So I'm basically trying to describe something that's four-dimensional in three-dimensional space. So what I could do is I can assign maybe colors to space. That's kind of weird. Assign different colors to the space. Wait, instead of colors, maybe, this is the same thing, right? So maybe instead of colors, maybe just assign contours to space. We can assign contours to space where the output. So back to this picture, I'm going to keep going back and forth between pictures. If I look at this picture over here, I see these numbers 10, 20, 30, 40, and 50 and stuff like that, right? So if I call this a function z is equal to f of x and y, in the context of this picture, including this picture down here, what is z? The elevation. It's the height of the mountain. And if I go to this peak over here, this is peak B. And that's over 50 feet or meters or whatever it is we're dealing with. That's the elevation. But I can just focus on this top picture over here and get a two-dimensional picture, two-dimensional idea of this. So when I take a look at this 20 over here, what does this 20 describe? Does it describe an X and a Y or a Z? It describes a Z. That says if I'm standing here in my map, I'm going to be 20 feet high in the mountain. Okay? So that's the same idea with this thing. If I'm at this point, ABC, let's say ABC was where am I? I would be 4, 3, 6. So let's say I'm at this point, 4, 3, 6. What can I say about my temperature there? So the temperature is given as a T function, T 4, 3, 6. And for this particular example, I kind of gave a formula already. So if you put these values into here, oh, this is backwards. I'm sorry. It looks like the further away from the corner, the warmer you're going to get. And that's not what I wanted. We can put the heater on the other side. Or make it go the other way. '61. So putting those values into here will give you a temperature, a particular temperature. And what I wanted was the farther you are away, the cooler you are. But I think the farther you are away, the cooler you're going to get. Or the warmer you're going to get. So maybe I'll put the heater on the other side. Sorry.
To get the formula that you actually wanted, would you have the initial output of the heater
Minus. Yeah.
that
Yeah.
expression?
Yeah. That's what I should have had. All right. Are you getting the feel for these functions of several variables? So these are the graphical points of views. We can also look at them from a numerical point of view. Your grade, for example, is a function of your homework, your quizzes, your exams, your final exam. What else do we have? I put J here. I don't know what J is. The lab. And then attendance. I don't care about attendance. Extra credit. So we can think about your grade as a function of 1, 2, 3, 4, 5, 6 variables. Right? And remember, the output has to be unique. So if you have a particular grade, your output is going to be determined by the formula. And so the formula kind of looks like this, I guess. 5% of your grade of your grade is contributed by the homework. 10% of your grade is contributed by quizzes. 40% for exams. 30% for your final. Let's say 5% is extra credit, and 10% is with the lab. So this is another example of a function of several variables. And the numbers that you put in would be those variables. Okay? And there's some examples here, but we won't worry about examples. Sometimes your examples could look like a table. Could look like this. I suppose we should have this as part of your notes. So as numerical examples. So what I do to calculate your grades is I find the average for your homework, the average for your quizzes, the average for your exams, and I put those values in and then put them into this formula, and then the output is your grade. And then I just change that into a letter grade. So that's how I calculate your grades. So this was an example in somewhere. I forgot where I got it from, but I should have used another example. Have you heard of wind chill factor? They have a table like this for wind chill factors. But I didn't pull that out, so let's use this one. So in this example, we can write this as the price of beef. Is there more? Did I miss something? So I think this is the cost that they're selling the beef. So this is your cost as a consumer. This is how much, if you were a store like Safeway or Whole Foods or something, and you're trying to figure out how much you're going to sell your ground beef, you have to buy the ground beef, and then you have to determine how much your income is, and then this is going to be how much you're going to sell. So for example, F of 40 comma 350, F of 40 comma 350 is this. So that says if the price of beef, if you as a seller have to buy beef at $3.50 per pound, that's the cost per pound, and then you have an income of $40,000, then you're going to sell your beef at $4.05. Okay? So that's how you can read a table like this. And I think that's how the wind chill factor works also. They determine the actual temperature and determine the speed of the wind. And so based on those things, they have a wind chill factor table. I think they have a formula associated with it too, but those formulas are usually really complicated, so they just have a table out for people to see. All right, so we took a look at the graphical representation. We're going to dive more into the graphical representations of these functions and then numerical representations of these functions. So now we should be able to take a look at symbolic, algebraic. Oh, let's do more graphs. What are these graphs for? All right, let's do an example where we take a look at a function and then we're going to plot some points. And so here, just to show you some graphs of things, You know how when we first started graphing in pre-calculus, we have a function and then we plotted points? So plotting points of this would be a little bit more complicated, but let's do something kind of simple. And then we'll have a computer like Mathematica try to figure out the rest of the stuff. So let's say you had a function x squared minus y squared. So f of x is equal to x, f of xy is equal to x squared minus y squared. So to plot this, we need to generate some points. So we'll plot some points. And one way to do this, and maybe in -4 by -4, -4 to 4, -4 to 4 set of axis, would be maybe just to plot some points here. And trying to plot this is kind of going to be weird, but let's say -4, -2, 0, 2, and 4, -4. I probably should do this backwards. So if I put x and y, if I put x is equal to -4 and y is equal to +4 into this formula, what am I going to get? What should I get? I get 0. If I put x is -2, y is equal to 4 into this formula, what do I get? -12. What? This is 12. And then this is -12. And if I put 2 and -2, that's also 0, right? So 0 for x and 4 for y, what do I get? -16. I think this is -12. Uh, 2 and 4, -12 again. And then 4, 0 again. Is that right? Okay. All right, we can fill in the rest of this table. And I just need one more 0. This is 4. $16, 12, 12 or 4? 4. Positive, so this must be negative. Oh, you can fill in the rest of this table. In any case, what you would have is a set of triples that would refer to your x, your y, and then all these numbers in here could represent your z values. So in terms of trying to graph our function, what we could do is we can find these points and then see if we can put them in the graph in x, y, and z terms. So for example, if I take, let me just circle this one right here. This has a -2 for x, a 0 for y, and then a 4 for z. This could be 1 point on this graph. And then I can have another point on the graph. Okay? So back in pre-calculus, when you first started to graph functions, you plotted points. You found an x, you made up an x, you found a y value. and then you made up another x, and you find a y value. So here, you're going to make up an x and y, and then you're going to find a z value. Now, to try to put all this together, your x and y is going to form like a grid in 2 dimensions, and then your z can determine the height, and where it's positive, it goes up, where it's negative, it goes down. So, let's see, I think I have some graphs here. Here are some points that are, if you look at it from the top, it's just a random grid of points. But if you put them in space, they kind of look like they're doing something. How did I generate my points? Oh, let's see if I slow it down. So if I take a look at the points that I got, that I started with, I just have -2, -4, -2, 0, 2, and 4. So I really just have, how many dots do I have? 25 dots, right? And then so if I look at that from a 3-dimensional perspective, I'm not going to see very much out of this, out of these dots. Can you even see the dots on the screen? So what we could do is, or what we kind of did in pre-calculus, we plotted more points. And so if you plot more points, you get to see a little bit more out of your picture. So with this, I think you kind of get the shape already. Can you see the shape a little bit better? How would you describe the shape? What does it look like? No? It's like a saddle, right? And so you're really not going to see that until you really plot more points. And once you've plotted more points and get an idea of how this thing looks like, then you can probably conclude that this is, in this case, in fact, going to look like a saddle. But plotting a lot of points is not really realistic here. By the way, what's the official name for this saddle? You remember? What? No. That's an even more unofficial name. Hyperbolic paraboloid. Hyperbolic paraboloid. So really, if you're going to plot points, you're going to need to put an awful lot of points to get a visual of how this thing might look like. Okay, so this, based on the points that we were looking at, looks like a saddle, also known as a hyperbolic paraboloid. Remember, the paraboloid part is because the x and the y are squared and the z is not. Now, if there was a plus between them, then it would be an elliptic paraboloid that we've already seen. But since there's a minus, it becomes a hyperbolic paraboloid. And the hyperbolas come up when we take what's called a level curve. So let's take a look at a level curve. What are level curves? So let's use the same function. I'm going to alternate now to z is equal to x squared minus y squared. And a level curve happens when you cut your surface with a level z is equal to a constant. So, for example, we've seen these examples before, I think. Z is equal to 0. 0 is equal to x squared minus y squared. And that turns out to just be two lines, right? Z is equal to 0. We get two lines. Z is equal to 1. Looks like a hyperbola. The question is, which way is it going? Is it going up or down? So, to check if a hyperbola is going up or down, I just pick a number or pick a point. Let's say when x is equal to 0. When x is equal to 0, I'm looking at when x is equal to 0, I'm looking at the y-axis. So when x is equal to 0, I'm looking at the y-axis. Is this ever going to work when x is equal to 0? I have 1 is equal to negative y squared, so I know that I'm not going to intersect anywhere there. So if I let y equal to 0, if I let y is equal to 0, then I have x is equal to positive or negative 1. So I would be opening up sideways. And so this would be your contour when z is equal to 1. Z is equal to 1. Does this look familiar? I mean, aside from getting nice contours like this is like that contour map of a mountain, right? This looks like, kind of look like that mountain. Z is equal to 2. 2 is equal to x squared minus y squared. If you divide by 2 on both sides, you'll just have another hyperbola. Z is equal to 2. And you can also go negative. Z is equal to negative 1. Negative 1 is equal to x squared minus y squared. Now, if you're used to seeing the hyperbola with a 1 on the other side, you can just multiply both sides by negative 1. And then you'll just have a parabola opening up the other way. So these are your contour plots for this surface. Which means if you take that surface that looks like a saddle and then you make your cuts at the xy plane, a little bit below the xy plane, a little bit above the xy plane, you're going to get these things as a result. So your task is to be able to make the relationship between a three-dimensional graph that may be difficult to see And then imagine cutting it with a plane. And as you cut this with a plane, you're going to get a resulting curve, right? So what's your resulting curve going to look like? Oh. See if I can do this. So as you make your cuts, you're going to get the resulting curve that's going to be your level curves at the different levels. Okay? In fact, there's a standard way of looking at this, and they look at, it's called contour plots. If you look at any sort of graphing program, you could take a look at the contours. And the contours would look like putting all this stuff together. And then if you want to follow that up with colors, you can use what's called a density plot. That's harder to see. Kind of like that temperature plot that we had. Usually it's lighter where it's higher. So it's lighter on the sides over here, and it's darker where it's less. So it's dark over here because it goes negative. It's dark towards here, but on the sides over here it gets lighter because that's where it goes positive. So this is another way to view your plots. Okay? So some of your practice in your homework and maybe a quiz sometime next week will be asking you to find the shape of the graph by looking at the different contours and things like that. If you have a three-dimensional graph, z is equal to something, I might be asking for level curves, what happens at this level or what happens in all levels, and then you have to try to come up with a contour plot, which means you have to be comfortable with the conic sections, because these things, the result that you get after you let z equal to something, a lot of them will look like your conic sections. I mean, a lot of them will look a little bit more complicated, but most of them will look like your conic sections. All right? All right, so that's it. We have some labs due the next day or two, so make sure you check your WebAssign and get those labs done.